So I think that's really what's biting us here. The data types, the serialization of objects sometimes, because they are operating here on their one native Java language. So that seems to be a major factor for people. And it seems to be easier for them to think that way. I personally, when you know me, I myself am a little bit surprised about that. I take SQL any time for that one, but particularly for that kind of task. Honestly, for other tasks though, like the data mining task, it actually is easier. But for that one, I would think the SQL query is much easier, no doubt about it. But nevertheless, you see a lot of people that like this paradigm. It's interesting. Maybe we're doing a bad job in database education, I'm not sure. Well, so now how do we parallelize or execute those functions? So what does the compiler have to do? So for parallelizing map, that's trivial, right? It's just, there's no dependencies between the records, so just span as many nodes as you have machines available at that moment. Then for reduce, and of course you want to worry about some trade-offs for split communication and so on. Then for reduce, that's also known business, right? Reduce parallelization is known business. The input is partitioned across all nodes by key, and you can locally group by key via sorting or hashing. That's some kind of decision that you could make, but in general that's known business, and that's how Hadoop would do it. Parallelizing code group, Hadoop doesn't have it, but it still would be simple, because you just, it's analog to reduce, but the only thing is you have to treat both inputs in the reduce function, and you interleave the streams in a zigzag fashion. And some people, when they implement joins in Hadoop, they actually do this now in their user code. So that's how you can actually teach Hadoop to do joins. The only problem is then you make your parallelization explicit, right? So you make it really explicit in your user code. Whereas the original idea of the MapReduce programming model, just like the Zorzor model in Google, was to actually hide the parallelization. You don't have to worry about it. But in this way, if you do it in the user function, you actually violate that principle. And you actually, what we are taking advantage of, we can optimize it now. So in a Hadoop environment, if you make it in the user code, you can never optimize it. So then executing the functions for match, there's choices. So for parallelizing match, and those choices are familiar to any of you from database optimization or runtime, right? I'm sure DB2 does several of those strategies here as well and chooses them in the optimizer. So parallelizing match, you can either partition both sides on the key, or you broadcast one side, which is similar to parallel join optimization in the database. Or you could do a sort and merge and hash on one side, which are choices that are similar to the local join optimization in the database. And again, for parallelizing a cross product, you could do a broadcast of one side doing an asymmetric fragment replicate join, or you could do symmetric fragment replicates, or you could use shuffling rings to move the data around. There's various ways of efficiently implementing that, and of course they all have a value. So there's some optimization potential here, but a lot of that can only be done at runtime. So that's now the next issue. So if we want to optimize across pacts, then basically pacts have required partition and sort properties. And if we know that those are preserved, and that's things in relational we know that very well, and that's what we exploit all the time in the optimizer, right? If we can infer those, then we actually can be more efficient. We can get rid of some of those hashing and reshuffling stages that Hadoop is doing way too many of. So that means some global optimization can make different choices in local optimization. So a locally more expensive choice could establish a partitioning, as you all know, they could be reused. And this requires, however, a way to invert properties, which in this model is much, much harder than if you have a well-defined set of operations like the relational algebra. So in this way, one way would be, and that's also done when you do use the defined functions in databases, right? You would have to give some additional information. That's really what you need here. Additional informations like are functions associative, commutative, or holistic, or things like, which is very important in this case because we're talking about partitioning the key properties. Is a key preserved, right? Do we have the same key, a super key? What is a function for these unique keys? If we have that information, we can exploit that. So that's actually business as usual. It's just applying it to this different space, but that's not, from a research standpoint, not really that much of a novelty. And of course, you would do a top-down optimization, propagate the properties, and then select a plan. The big issue here is result size estimation, because that's very hard since we have to deal with black box operations, right? We don't know that this is a filter. We don't know that this is some kind of clustering or whatever is going on in this first order function. We know the input sizes, right? We have DFS file sizes. We make no number of blocks, and we could even try to get some information about the keys. But that's pretty much it. So right now, we have not really embarked too much on it. Right now, we actually do something like hints. We annotate the functions. But what we want to look at now in the next year and 2 years, a PhD thesis is looking into, or 2 PhD theses I should say, look into robust optimization, where we generate initial robust plans, which are then adapted during runtime. So that is, we take the input sizes for the first functions, which you can roughly estimate, and anything else later is robust or will be adapted. Let me show you in more detail what I mean by that, which is a research challenge. So we have that problem that we have limited information during query compilation. Right? We are in a hostile environment here. We have insufficient or unreliable statistics. We have this dynamic cloud environment with machines coming and going, and we have, in many cases, long-running tasks. So there is no way to find an optimal plan, or even something near optimal at compile time. And what we need to do now is we need to, what we want to do here is to apply a very different query optimization strategy, which actually would also apply to traditional databases, by the way. So that's maybe also interesting in a generic DB2 context. So the idea is to optimize robustness instead of optimizing performance. And that means we want to minimize risk. So let me give an example here on this chart. So let's say on this chart here, we have 2 cost functions where the cost depends on the problem size and available resources. For simplicity, just think cardinality, but of course there's other parameters. But here we have a green function, maybe some kind of nested loop join, and a blue function, maybe some kind of hash join, just to give a rough intuition. And now we can associate a expected value of the cost, right? Which is traditionally in databases, in cardinality estimation, we do that. We compute the cardinality estimate, which, however, would be a certain point, like this point, for instance, could be our estimate. And then based on that point, we actually would choose the green plan, right? Because the green plan is cheaper. However, if we do not consider the estimate as a point, but based on the probability distribution of the input, if we have some assumption on that, we consider that as a range or as a probability distribution, right? The estimate has a mean, and it has maybe some standard deviation or some kind of function, then we can define robustness. Robustness then is, for each given plan, is the product of the cost, it is the integral, we're doing an integration of the cost function here,